Yeah, maybe somebody want to just, oh, sure. Okay, great. So I don't have any kind of introduction prepared. We need this to be full screen. We have Parker here. He's a guy. He came from Michigan.
Yeah, so maybe just to get a bit of a background on you guys. Are you guys more roboticists or machine learning engineers?
Good question.
Depends on who you ask.
Is it a both? Okay, cool.
I'm a roboticist.
Okay. So yeah, my background is primarily robotics. So a bit about myself. I'm currently a PhD student at the University of Michigan with Professor Ron Masudovan. Our lab primarily focuses on things like robotic safety. So how can we guarantee, like, if we have some representation of the world, like, can a robot safely move without hitting into things like people or objects? I'm sort of the black sheep of the group. So when I joined, I immediately started criticizing everybody that how could they possibly be safe if you couldn't perceive the environment very well? I'm going to show you guys some of the early experiments I ran to prove my point pretty quickly. And so, yeah, this is sort of the culmination of my research during my PhD, focusing on like what actually allows robots to succeed at tasks. Before I was at Michigan, I did my master's at ETH Zurich in robotic systems and control with Professor Marco Hutter. So I was using quadrupeds a lot and doing mobile manipulation. Also noticed a lot of failure cases there, so that sort of motivated also this work that I'm working on now. So, for those of you who've worked in robotics, you might have, even for those of you who haven't, you might have seen some of these videos of robots doing crazy things over, the past 2 decades. Boston Dynamics' Spot is doing some crazy stuff, Animal, the leather-legged robots are climbing mountains. And that would lead you to believe that maybe robots, have come a long way, but there's still a surprising number of failure cases. And this is some of the early work we did where, just this simple task of legged locomotion, something that we would assume to be very good, still suffers greatly. And the challenge with this is that the robots don't learn anything from these failures. So the robot's fall in has to be, recalibrated by a human, and it'll do the exact same thing next time. Sort of in contrast to, animals and humans, where we have a failure case and we learn from it, right? So the dog's able to fall, get back up, and continue moving. And same with humans, right? We interact with the world and we learn from these interactions. And over the past 2 decades, robots have gotten very good at navigation, so moving around their environment, but still struggle at interacting with their environment and learning through these interactions. So my work primarily focuses on combining planning and perception in this way that robots can first see their environment and use these perceptual representations in order to act effectively, like seeing that there's ice and maybe being more careful to walk across it. And likewise, using planning to say, if I'm uncertain about the world, maybe I go take another measurement or a safety maneuver or something in order to act, in order to increase the accuracy of these perceptual representations. So there's a couple of challenges with doing this, and the first is with computer vision that you guys might be familiar with. So on the left, we have an RGB image from a robot's perspective, and on the right, we have the semantic segmentation output. And here we're estimating different terrain classes where bright green here is grass, the dark green is asphalt, and then this green is sidewalk, and then brown is human. So we're going to see that even for small camera changes as the robot moves around the world, we're getting these very noisy semantic segmentation estimates. And so the way that robots often perceive the world is through vision and these semantic segmentation estimates. And so if these are noisy, how can we expect the robot to interact with the world or learn from these interactions visually? And so the first thing we have to tackle is how do we model this uncertainty that allows us to filter out the semantic segmentation noise effectively. The second is we previously saw robots still fail a lot at various tasks. And so why is this? What causes these failures? Well, I argue that it's an incorrect perception of physical properties. So here's the coefficient of friction that causes the failure in legged locomotion. In this case, right, it's not the steepness of the incline of the hill that causes the robot to slip back down. It's the properties of the granular surface it's walking on. Similarly, for manipulation, if a robot drops an object, it's because the contact points, the contact closure is usually incorrectly computed, or the object is too heavy for the robot to lift. And so for these robotic tasks to have increased success, we need to be able to estimate the properties that dictate this success. And for each task, which property matters, that's a question we have to ask ourselves. And finally, robots typically use vision, but there's many, many cases where vision isn't enough to learn about the world and interact with it, right? So there's areas, with visual occlusions, poor visibility, low lighting conditions, and this causes, vision to be a poor sensing paradigm for robotics. And so we want, multiple sensing paradigms to work together. Similar to, humans, we can touch stuff, we can feel stuff, we can find our way around a dark room, not using only vision, but different senses. And so my work tackles, addressing these research gaps. If we were able to address these gaps, robots can do all sorts of really amazing things, right? So robots would be able to help with crisis response. So we could have robots assisting first responders, seeing how their actions affect that crisis response and modifying their actions to be better assistance. For in-home assistance, right, each person is different, each home is different, and the robot can interact with its environment, interact with the humans, and learn how it can, better serve these people. For delivery, each package is, unique, different size, different shape, different weight. To traverse from a van to a front door, each house is different, and so the robot has to learn how to interact with all these elements together. And finally, for exploration, for things like mining and subterranean exploration, rural exploration for forest and agriculture industries, the robot has to be able to learn about its environment and prevent things like, in this case, like a locomotion failure. And so the contribution of my work in my PhD primarily focuses on creating these perceptual representations that allow for a robot to learn about its interactions with the world, primarily by modeling these physical properties that the robot has to understand in order to have task success. So my talk is broken up into two sections. The first is going to be how we can use perception to build up these models and then use these models in order to act effectively. The second is how we can then act effectively in order to create more accurate perceptual models. So a bit of my work in this area, in terms of perception, I have focused on semantic mapping, property estimation using different sensing modalities, and all of these run on board the real robot in real time, so with limited computational resources. And in terms of planning, I've primarily focused on like locomotion and like manipulation, active perception, and using tactile sensing modalities for improving sensing. And I'm primarily going to focus on these two works. So starting with the first portion of the talk, C to Act. This work is primarily focused and motivated by work we submitted to RAL in 2021. So typically in robotic perception, for those of you who aren't familiar with this area, we start with some sensing inputs. So from an RGB camera, might have depth images, we might have LiDAR, tactile sensing, and in this work we're primarily going to focus on vision. We can use these sensing inputs to build a perceptual representation of the world, and this could be a semantic map of any form where, here we have ice and snow classes. And so the algorithm we developed for this work starts first with that data collection step, and we assume we have some semantic segmentation network that for each RGB image, we can get an estimate for each pixel of the Turing class likelihood. We can project that depth information to create some geometric model of the world, in this case, a contact surface mesh. And then we can project that semantic segmentation images onto this geometric surface, and that creates consistency between these semantic segmentation images as the robot moves around. This geometric consistency allows us to then use Bayesian filtering in order to approximate these semantic class estimates recursively. And then in this work, we would likewise present a method that allows us to probabilistically relate these semantic class estimates to physical property estimates. And in this work, we're focused on the coefficient of friction, but we show in the next work that this can extend to a bunch of other tasks as well, properties. And so in this work, we start by first showing how we can model physical property uncertainty using only visual data. And we'll build upon this in the next section. Great, so let's go back to the semantic segmentation issue we saw previously. So as the robot moves around, we get these very noisy semantic segmentation images, and the first challenge we have to overcome is, how do we even account for this noise? For whatever reason, this clicker isn't working very well. Well,
the batteries.
Yeah, I have an extra set, which is nice.
Always come prepared.
Oh, that one doesn't fit. There we go.
So there's some kind of assumption somewhere that, like, although it's noisy, the semantic segmentation, it's still like, there's some properties of the noise that are going to allow you to, through a fusion process, get the right thing.
Exactly.
Unbiased. So
exactly. Yeah.
Very bad way.
It's unbiased, so we are, estimating the true semantic class more than randomly.
Right.
Is the baked-in assumption here. And so for much of, Bayesian inference, that's one of the things you have to consider. And so, from these semantic segmentation images, we really have to tackle two problems. So the first is, how can we filter out these semantic estimates? And the second is, how can we then estimate physical properties from these semantic segmentation estimates? So we can break this down very nicely into two problems. So the first is, how do we estimate these semantic classes using Bayesian inference? And then the next, we can show that this Bayesian inference for semantic class estimates works really nicely for physical property estimates. So let's tackle that first one. So we're going to use Bayes' theorem here because we're doing Bayesian inference. So we're going to start with some prior on the semantic class for each region within our geometric surface. So this is going to be the robot's belief in the semantic class before it gets new information. We then get a new observation in the form of that semantic segmentation image. And interestingly enough, we can model this observation in the form of a categorical distribution for each pixel within the image. And then we can use Bayes' theorem to compute the posterior or the robot's belief in a trained class after it's taken the semantic segmentation. And so what I noticed in this work is that if we model that observation as a categorical distribution, there's this very nice theorem in probability theory called the conjugate pair theorem that says there's a particular distribution for that observation called the prior distribution that when you use Bayes' theorem with this conjugate pair, so the prior distribution and the observation distribution, the categorical, the posterior will be in the same family of distributions as the prior. And this is really nice because this allows us to only update a closed set of parameters. This is really, really fast and really efficient to do. And so, the insight in this work is we're just going to actually use this conjugate pair theorem in order to do this filtering of semantic segmentation images. And it's actually surprisingly simple how effective, and it just really works. I'm going to show you like a high-level visual example of what we're doing here, but this is actually true to form in what we're doing in the actual semantic mapping framework. So we start with the semantic map, and maybe a region of interest is this region here, and we want to estimate what this triangle in the mesh is. And if we haven't seen it yet, we're going to initialize each class of interest with this vector here, a vector of all ones. So this means we haven't seen anything yet. And then we're going to note that the probability density of each of these classes is going to be directly proportional to the normalized index of that class within the vector. So now let's say we get an observation. And maybe that observation tells us that this region of the map is most likely grass. Well, we're simply going to index that value of the vector for grass by 1, right? And then once again, that's the posterior probability density is just the normalized value of the index for that class. We reset that as the prior, and maybe we get a new observation, new semantic segmentation image, right? And to compute the posterior, once again, look at the most likely class for this region, and maybe this time it's asphalt. We index the asphalt value by 1, and once again, that posterior distribution for each class is just corresponding to the normalized value of the index for that class. And so, this might seem very simple, but it is very true to form for these probability updates. Yes?
So if I understand correctly, you're doing like Thompson sampling essentially on the indices.
You're doing what, sampling?
So like when you get the correct value, you add probability, like a bit of distribution, basically.
Yeah, actually, so when we index by 1, it's actually in probability theory, there's this notion of like that closed form update on this distribution. So the distribution we're using to model the prior and posterior of the class likelihoods is what's called the Dirichlet distribution.
Yeah.
And you can simply update the Dirichlet distribution parameters here by indexing the most likely parameter if you're drawing from a categorical distribution which we're assuming the observation is drawn from. Does that answer your question? Great. All right, so now we have this recursive.
I thought you were going to maybe mention something about this, but it seems so either your robot is still, and then you know exactly that your region is not moving, or you have that other geometric part that you talked about where you're actually like doing some kind of slam thing to figure out exactly which piece of terrain where you should look to do the fusion part, right? Like you want to do the fusion in space, not in pixels.
Yeah, that's so we project everything, the semantic segmentation images, onto this geometric representation and actually do this filtering for each discrete element. So in this case, it's a triangular mesh element. You can do this in a voxel if you're doing a voxel map, or a Gaussian if you're using Gaussian splatting. So you're doing this within the space because that allows you to have geometric consistency as the robot moves around and sees different parts. And this was also one of the benefits, for instance, when we're working outside and there's different lighting conditions from different angles. This helps sort of filter out those issues we see with data distribution data and the networks we're using. So that's how we can do, Bayesian inference for this trained class estimation. So now how can we estimate physical properties from these estimates? Well, one of the insights we had in this paper is that these properties of interest are often material or class dependent, right? So when we look at ice, we think of ice as being slippery. When we look at concrete, concrete's quite rough, right? So we can we can decompose these properties and they can be dependent on class. And so to build this class-wise friction model and this work, we went around the University of Michigan and the Ford Robotics building where I do my research, and we collected a friction data set for a variety of classes of interest. So things like pebbles and rocks in the outside walking yards where we use legged platforms to climb stairs and stuff. Concrete and plastic in the lab that I actually do my research, the walk lab. Things like carpet and flooring out in the atrium of this building, and a variety of other outdoor classes of interest that the robot might encounter. And so in this data set, we took approximately 10,000 friction measurements across all classes of interest, and what we found in this work is that, interestingly enough, the Gaussian distribution represents this class model for friction very accurately. We tested other distributions, but found that this one actually outperformed all the others.
Is this like the static friction or the dynamic friction?
So we made an assumption here that we were measuring dynamic friction. We care about static friction, but dynamic friction is a lower bound on that.
Okay.
And so, if we can satisfy things like risk constraints over the dynamic friction, we can satisfy these things with static friction.
Okay.
And so, now for each class, we might have a different Gaussian that represents that class-wise friction model. And we can compute the mean and variance of that from our trained friction data set. This is open source if you're interested. So, for grass, we might have one Gaussian. For asphalt, we might have another Gaussian. And for the sidewalk class, we might have a third Gaussian. We can just add all these Gaussians together and then normalize that Gaussian mixture. And that could give us a model for things like the coefficient of friction for different areas in our terrain. And each of these would be weighed equally if the belief in each terrain class was equal as well. When that's not the case, each Gaussian mode is weighed directly proportional to that class likelihood of each terrain class. And so as the robot's collecting this semantic segmentation information, we're updating the likelihood of each terrain class, and then this can directly affect this Gaussian mixture model that allows us to then model the uncertainty with respect to physical properties as well. And so why do we care about doing these physical property estimates? Well, we want to avoid cases like this where the robot just walks across ice and slips and falls. We want to be able to have the robot see that and say, hey, maybe this area is slippery, maybe I should change my locomotion strategy in order to successfully traverse it. And so, this is our algorithm running on board the real robot. So we see the robot in the upper right-hand corner here. This runs in real time. And so we see it building the geometric model from the onboard depth camera. And then onto this geometric model, it projects the semantic segmentation information that it's getting. And then we can do that recursive terrain class estimation using the Bayesian filter that I previously showed. And again, we're doing that for each triangle within this representation. So it's very efficient and very easy to store. And then we can use that terrain friction data set that we collected in order to then estimate the physical properties of each triangle within this mesh. And for each triangle, we're storing a Gaussian mixture model. And shown here is just the expected value for that coefficient of friction. So, this method is quite expressive. It's quite lightweight, and it's very efficient to run online. And so, from this section, we can take away that in order to act effectively, we need to be able to estimate these properties of the robot's environment.
Is the expectation really the right statistic to choose for that?
We were just showing that for modeling purposes so that you can visualize it, but we do maintain the entire distribution.
But if you were actually thinking about like what gate to choose, and you had some, let's say like equal probability that it's ice, whatever, your expectation is going to give you something that's kind of middle of the road.
Yeah, exactly. So we use the expectation in actually the next demo that I'm going to show. But if you were to correctly do this with safety thresholds or risk-aware planning that we're currently working on a project now, you might want to do something more akin to like what's the integrated probability that if I step here that I'm within the friction cone, for instance. So there's more principled ways of approaching this that I think is an interesting future direction. Does anyone else have any questions?
Yeah, in the video, the robot was not using, it was estimating the friction coefficient, but it wasn't using that in its gate, right? In the video you just last slide. Okay.
Yes. Wasn't using it then. The next video I showed, it isn't going to use it.
Okay.
So that was, just a presentation of the work where we're just trying to estimate these things accurately. And we also did this in simulation and showed that these estimates are quite accurate if your visual model is quite good. So now we're going to discuss acting to see. So how can robots actually use different sensing modalities and more active sensing modalities in order to more effectively estimate these properties? And so this work actually we just submit to RSS and we'll be presenting on in 2 weeks. So back to your question, what happens when we use that coefficient of friction estimate? Well, it turns out that vision might not be the best modality for this. So here it's unable to distinguish between snow and ice, right? It thinks all that region is ice. And in fact, if we use vision alongside a novel traversability estimation method, which tells us whether a robot can walk in an area or not, and green says it can. If we use only vision for both of these methods, it incorrectly predicts that it can walk on the ice, and as we can expect, it's going to slip and fall. I think it maybe not optimized for videos, but anyway, you can see it. So if vision is incorrect, what can we do? Well, we can tell the robot to go take a friction measurement using the manipulator on board, and it can sense that, hey, maybe this region in front of me is quite slippery. So it can use that information to jointly update both the semantic class estimates as well as the property estimates, and then use these property estimates to switch to a more static, stable gate. And that allows it to effectively cross this icy surface without slipping and falling. Right, so now we can actually use these properties effectively when they're estimated correctly. And so going back to this algorithm, we had this method of data collection, and we were initially assuming that this was from vision. Well, now if we have an additional tactile sensing modality, we can actually estimate these physical properties directly, right? So the robot can go and touch it and see what it needs to learn. The challenging bit here is that by estimating or measuring these physical properties directly, we now have an interdependence between these semantic class estimates and physical properties. And so we can't just model the Bayesian inference over the semantic class. We have to model the Bayesian inference over the joint semantic class and physical property estimates. And so the contribution of this work is such a modeling paradigm. So we're able to model physical property and semantic class uncertainty using both vision and tactile sensing. And so for semantic class, we saw we had this prior, this observation in the form of a semantic segmentation image, and then that computed posterior that we're able to compute in closed form. We can do a similar thing for property estimation. So we have some prior, some observation, and some posterior. The challenging bit, as I just mentioned, is now there's an interdependence between these semantic class estimates and physical property estimates. So, previously we saw that, hey, maybe ice is slippery and concrete is not, and our belief in those classes affect friction. But now if I believe that, an area of this room is concrete and I go and touch it and it's quite smooth, maybe my belief in the class is, oh, that's not concrete because concrete isn't smooth. Maybe that's a different class of interest. So by taking a tactile measurement, we're actually updating both of these beliefs in both the semantic class and properties jointly. And so, we're once again going to utilize the theorem of conjugate priors because it allows for this nice closed form update of a closed set of parameters. So computational efficiency, and this can run on board a robot in real time. And we're going to use this to now model jointly that semantic class and physical property estimates. We have an issue. So remember last time I said we were modeling the coefficient of friction as a Gaussian mixture model. That is now our observation distribution. And there is no known prior distribution for the Gaussian mixture model. One exists because a GMM is in the exponential family, and for probability theory, we know that conjugate prior has to exist for any member of the exponential family. But there's nothing in the literature that shows, one such distribution. So in this work, we had to derive an approximate distribution for that conjugate prior. I'll show what this approximation means, but it works out actually very well and works quite accurately. So the distribution that we're going to look at is going to be modeling both the prior and posterior distributions for both these property estimates and semantic class estimates. And the observation is going to be that tactile sensing estimate now, where that's going to be drawn from a Gaussian mixture model. And so visually, let's take a look at what this is doing. So we're going to look at a general function space F. And we're going to look at a subset G, and this G is going to be the family of distributions of the prior distribution. In the paper, we show that this distribution is going to be what we call the Dirichlet normal inverse gamma product distribution, which is a bit of a mouthful, and I'm not going to show all the math for it here, but visually we can see what's going on. We're then going to get a measurement, and that measurement is going to be modeled using the Gaussian mixture model, and we can use Bayes' theorem then to compute the posterior, right? So what happens when we do that? Well, it turns out that using Bayes' theorem, the posterior distribution is no longer in the same family of distributions as the prior. So that leads to two issues. The first is that we have to continually recompute what that posterior distribution is, right? And that's challenging to do online. And the second is even if we're able to do that, it creates an exponential increase in the number of parameters we need to maintain belief over. So, even for like 4 to 5 friction measurements, this quickly becomes computationally intractable. And so to overcome both of these challenges, we can use a nice little trick called the method of moments, which allows us to functionally project that posterior back into the same family of distributions as the prior. And so by doing this, again, we're updating only a closed set of parameters, which allows us to do this really fast and really efficiently online on limited hardware. And so, and this enables closed form Bayesian inference or approximate closed form Bayesian inference, but we found, during our experiments, it tracks very well empirically. And so we can do this for things, not only like things like the coefficient of friction, but things like the force required to open a door. And so doors are multimodal, maybe it's push to pull or push to open or pull to open, and there might be some force associated with each of those options. And so the robot can have some, uninformative prior, let's say, of both push or pull being equally likely, as we're going to see here. And then it's going to do an observation, so it's going to push or pull the door randomly with some force. And once it gets movement, it will, see at what force it gets movement, and then it can update to some posterior estimate, and this posterior estimate corresponds to the robot's belief in how much force it requires to open the door, where negative is push and positive is pull. Another thing we did in this paper is we saw that we can, because we're modeling these semantic class likelihoods and physical property estimates jointly, we can actually use a tactile sensing measurement in order to improve semantic segmentation. So this was done both in simulation and in the real world, and we saw that, when we use tactile sensing, we see a significant increase in semantic segmentation performance compared to using only visual models. And so, the takeaway from this work is that in order to accurately model the robot's environment, the physical properties, we do need these additional sensing modalities, and these are more active sensing modalities, so the robot has to stop what it's doing and actually go and plan how to take these measurements. And so my vision going forward is really to, have robots achieve long horizon autonomy in dynamic environments by being able to interact with their environment and learn from these interactions. So, being first able to see to act, and then being able to act to see it, and maybe reduce the uncertainty. So my current projects involve active perception. So how can a robot, move around its world autonomously in order to figure out how best to minimize uncertainty and learn about its environment? And other projects I'm looking at now involve using reinforcement learning in order to now take this property data to more effectively accomplish a variety of tasks. So I also want to thank my collaborators, without whom none of this work would be possible. So first and foremost, my advisor, Professor Ron Basudovan, and all of my lab mates and exterior PhD collaborators. I talk with them, form opinions about robotics, argue with them all the time, but they're great and I love working with every one of them. And then I've worked with a variety of master's students that I've mentored throughout their degrees, and a bunch of undergrads as well, without whom, this work wouldn't have been possible. I love working with all these guys. They're fantastic, absolute all-stars, and they're going off and doing amazing things now. So I would be remiss if I didn't give them a shout out for all the work they've done. So that's my talk. I hope that your takeaway from this is that in order to be more effective in the world, robots need to be able to interact with their environment and learn from these interactions like humans and animals do. And that to do this, we need to be able to see to act and act to see. So, thank you.
Great. I had a question about the second part. I think I didn't quite understand exactly what the observation model actually was.
So the observation model is that Gaussian mixture model that we derived in the first half.
But how are you actually getting Gaussian mixture as an observation?
So it's not.
So it puts its nose on the ice.
Yeah. So it doesn't get a Gaussian mixture as an observation. What it gets is a sample of the coefficient of friction that we're assuming is drawn from that Gaussian mixture model. So using only vision, we're estimating like, hey, what's the likeliest distribution for the coefficient of friction, and that measurement is going to be inherent.
Right. Okay. So the observation itself is a coefficient of friction, and that's the thing that you're fusing with your posterior to try to get the Gaussian mixture over the classes.
Exactly. Yeah. And by updating that prior and posterior distribution, you're likewise updating that observation model. And so you're saying like, hey, what's the best observation model that describes the measurements I'm getting? So usually you take this over several measurements. So when it's on the ice, it's maybe getting like 7 or 8 measurements of that coefficient of friction.
Okay, but I guess the problem is, so I'm just trying to understand exactly. So in the semantic segmentation case, you just assume that you're getting one class that's output by your semantic segmenter. You're not fusing the whole output distribution from the semantic segmentation. You're just assuming the most likely class is correct. But then in this case, when you get a friction reading, it doesn't uniquely correspond to one specific output class.
Yeah.
So that's the problem. Because you actually, like the friction information doesn't directly give you an observation over what class.
Yeah, exactly.
Yeah.
So by modeling these things jointly, it allows us to then estimate, like that coefficient of friction measurement jointly
Right.
is related to one, the class of interest, but two, the model of friction of that class. So
That's right. So like if each one of those is a Gaussian like you showed, then each one's going to have maybe support under the specific reading that you just took.
exactly.
And you want to update your posterior like proportionally to the support that it would have had under that distribution.
Exactly, yeah. And so for things like if we look at that ice demo, if I can maybe go back for a second. Oh shit. Let me just share my full screen here. Yes, demo. So if we look at the prior before it takes a measurement, so if we look at the belief in ice, for instance, the belief in ice is quite low compared to snow and concrete, which are quite high. All the other classes were basically uninformative. And then we see that the bumps corresponding to concrete, snow, and ice are here, weighed based on the normalized value of these Gaussian weights. And so when we get a friction measurement, it actually is sampled here. And we're getting several, so you can assume that like there's 5 or 6 samples along here. And what this, distribution update is looking at when we're computing the posterior is saying, well, if I'm getting all my samples here, but this is the, Gaussian mixture model, the observation model I'm seeing, like this is probably the incorrect, like observation model, right? So it's probably focused more like a higher Gaussian weight for that mode. And we see that in the update here. So we said, okay, if I'm getting all my samples here, like it might be the snow class or the concrete class, but it's much more likely to be that ice class that I'm getting all my samples from. And so this allows us to, both estimate semantics as well as properties. And so we're seeing that the new property estimate is corresponding more and more to ice.
Do you think it's limiting that you have this like fixed set of classes that you have to predetermine?
Yes. So one of the future directions that kind of other students have been mentioning and I've been thinking about recently is we're dealing with a fixed set of semantic classes that we had to go and take friction measurements for. So what if we were to use something that's like a continual space, like VLMs maybe?
Yeah. Everyone's doing it.
Yeah, and then the challenge then becomes, now that we have this continuous set of possible semantic classes, how do we then create the model from these classes to something that's more, continuous but over a fixed support, like the coefficient of friction or the force required to open a door. One of the challenges is even figuring out what properties matter. So one of the things that I've been looking into is like, if a robot has to walk this way to navigate, and it comes up to a chair, rather than replan and go around the room, can it learn that like, oh, I can push a chair out of the way and keep walking? Or someone brought up yesterday, like a plastic bag in the street, can it know that like, whatever, it's not gonna be that bad, like I could step on it or push it out of the way and keep walking. So there's a lot of interesting directions here, primarily focusing on like, that continuous model for semantics, or even figuring out like what properties of these classes matter. So there could be subsets of that, continuous semantic space that you care about different things than others.
So would you say that the main reason for choosing to discretize stuff, let's ignore the fact that it's slightly just easier from an engineering perspective and have limited time to do the project.
Yeah.
But would you say it's due to the way it's incorporated within the control of the robot? Like, I noticed that in the demo you had like 2 modes, so you had like a hybrid controller instead of, for example, like a one controller that just has a continuous parameter. Except that the friction is like, seems to me like there's a good reason that you chose it to do like this, but it's theoretically not required.
Yeah, see, you're hitting the nail on the head. So I started out, I don't know if you guys know the Animal platform, the Animal quadruped. So I started out working on that, and I actually worked at Robotics for a while. So for that machine, you could actually write out the friction cone constraints for the feet. And so my original idea was like, hey, let's do that. Like we have these friction constraints now. Like, what if I could take the expected value as an initial example, or I could do something like a risk threshold where I say, okay, well, if I have this particular force at my feet, which corresponds to this acceleration, then maybe, like, let me estimate if this is the coefficient of friction, right? So let me integrate the probability and then integrate the probability that I'm within the friction cone and maybe set some constraint on that. That's where I want to go. The issue is on the Spot platform, you do not have control of basically any low-level stuff. So I think they recently, very recently, like within the past week, opened it up so you could spend like $40,000 and get access to JointWorks and like write your own controllers. But at the time we were doing this, you can really only be like walk forward for this distance, walk forward at this speed, and then you can set those discrete methods.
Okay. Yeah, I think this is sort of related because there's a problem I could imagine coming out of here where if you were constrained in resources or you didn't have the right foresight and like your discrete set of classes somehow didn't cover the right range of coefficients, you could end up with like measuring a coefficient that was just low probability for all of the classes that you had, even though you would actually be measuring maybe extremely accurately and precisely the real coefficient of friction.
So this is another really, man, you're asking some great questions here.
Oh, thanks.
So I've been discussing this with a student who recently graduated. I think he's starting his PhD again soon. So we kept talking about this notion of like, why classes? Like, what are semantics? And the thing that we kept arriving at least with this line of work, was like, those classes are determined by the coefficient of friction, right? Or properties. So, you know, if snow and ice have the same coefficient of friction, do I really care if it's one or the other? But so we were even talking about using some active perception approach here to like say nothing about the classes. Be like, I don't care the classes. I'm going to start from scratch. I'm going to look at things and I'm going to go and like touch them and feel them, and then slowly build up an understanding of these classes based on those properties. So like, hey, okay, this is visually similar to like a region over there. So maybe these are the same class, but I don't have a name for them. Oh, like let me go feel this. So this is visually, like tactilely distinct and also somewhat visually distinct. And so you can build up this set of semantic classes based on the properties associated with it. And these can be other, like, we're only using one property here, but the theory extends to multiple properties quite easily. And so things like, you know, pushability or like malleability, like can I push things around? Okay, well if I can push this and it's visually distinct and has this feel to it, maybe this is its own class, right? I know there's a lot of other classes that look like it around here. So that was one idea we had, and you know, an interesting future direction I'm thinking of going, and maybe something that ties in really nicely with this concept of like open sets of semantic classes as well.
Yeah, it's an interesting challenge. I feel like this is a thing that people struggle with in a lot of domains, like for all kinds of stuff. I mean, your example is a physical interaction.
Mm-hmm.
I mean, you could argue maybe that a huge benefit of the recent like vision language models is essentially doing what you're describing, but for their own little domain of like, I would like images to correspond to words.
Mm-hmm.
I don't know, you know, maybe I don't have a breakdown exactly of what is an image of a dog playing in a field, but eventually I'll get there from doing the right contrastive learning or the right data gathering, and here you're looking at a different set of things.
Yeah, and I mean, I think we're even enforcing a bit too much structure on that. Like we're saying, oh, we know what these things are in the world, so it has to correspond to our vocabulary rather than a robot building up its own vocabulary. Like maybe it doesn't care about things like the lights in here, but it's like, oh, the things I interact with that dictate task success are things like the floor, things like these chairs that I have to push out of the people so I don't want to hit them. And you kind of learn what's important and what doesn't matter. I think that's an interesting direction forward, and I wonder, you know, with all this increase in learning and robotics, if that's one of the directions that we might see in the future, kind of softening the prior estimates we're throwing on these robots and allowing them to build this up more naturally.
Just thinking about the, I guess I don't know that much about robot dogs, but maybe I know some, I don't know about anything, but it's also possible. But the Bayesian inference problem that you're solving here is like somehow intriguing to me. So I'm not 100% sure I'm like understanding or convinced why you need to do the fancy thing that you're doing. Like you can, why couldn't you have had a Dirichlet prior? It's like, oh, so you have, you get this friction measure, it's 65, okay? You look at all your classes, you look at the likelihood of 65 under all those classes, you take those values, you normalize them, you have a you have a categorical distribution. Why can't you just fuse that with your existing posterior? Do you follow what I mean?
Not quite.
So like, it's possible that I'm just not understanding the problem.
I also
correctly.
will say I have not put any of the math in here because I had 30 minutes.
Sure, but so first of all, when you're doing just the semantic segmentation part from the vision part, are you taking the entire output distribution that's coming from your semantic segmenter, or you're just taking the maximum value?
Currently, we're just looking at the maximum.
But you don't need to do that. There's no reason you need to do that.
You can take all, because
the math works out just the same.
Yeah, exactly.
Yeah.
Yeah. So you can treat that as a multinomial and just be like, okay, I have some,
Instead of those being integers, they would just become non-integer values that you could still normalize. Like instead of 322, it would be 2.8.
So you just add and be like, oh, I believe this is 50% like this.
Exactly. So you add half and half.
Yeah,
right?
exactly.
But so imagining that you can do that you could do closed form like inference with the Dirichlet prior using that thing, then it would seem to me that like your friction estimate could be used to give you the exact same distribution over your classes by just looking at the likelihood under those prior distributions of each of the friction values.
So maybe I'll explain. Yeah, maybe I'll add some more math here because this will help explain it a bit better, perhaps. So initially, when we only are using vision, we can model the likelihood or the probability of a particular terrain property, in this case the coefficient of friction, using these alpha values. And that was that vector that we're basically adding that observation to. And then, this just equates to this Gaussian mixture model where the weight of each Gaussian is the normalized value of that alpha value, the vector, and then this normal distribution. And the way we get this normal distribution is computing the mean and variance from our terrain friction data set. So the thing we noticed in this work is that these values might actually change in the real world. So like I measured a patch of concrete in the lab, but that's not necessarily indicative of the concrete elsewhere. So like this concrete is like slightly smoother than we have. There might be a concrete that's more, coarse.
Mm-hmm.
And so what we notice now is that, well, we're not only uncertain about the class likelihoods, we're uncertain about these two parameters as well.
Yeah.
So what we've done here is said, let me just scroll down to here. Yeah, here we go. So we say, okay, we have this model now for the coefficient of friction, and now we're going to treat both the likelihood of each class as well as the mean and variance of the friction model for each class as being unknown variables, right? So we might have some prior estimate on these, but this is our observation model, right? So when we take a friction measurement, given some values, we're getting an output for that. And then what we're saying is, well, if this is our observation model, this Gaussian mixture here with these three values being uncertain, we're trying to find a prior distribution for that. And so that prior distribution has to be conjugate prior. And what we found in this work is that when we were deriving it, so
sorry, maybe just one point of precision before you go on. So how are you actually ending up updating the mean and the sigma?
That happens after we get a friction measurement. So we start with, we can initialize this from vision. So we can say like, hey, how likely am I seeing these classes? And then these are using the train friction data.
So the problem is that you're uncertain on both sides.
Yeah.
If you get a friction measurement, you're not 100% sure about what the class of the thing is, and you're also not sure whether the friction associated with that thing is right.
Exactly.
It's like wiggly on both ends.
Yes, and then there's the reasons that it is wiggly and the reasons we notice is wiggly.
Yeah, no, I think that makes sense.
So when we have this as the observation and we're uncertain about these three things, we can use this to model that conjugate prior, and this allows us to say like, this first term here corresponds to the likelihood of each class, and then these terms, each of these normal inverse gammas here, correspond to our belief over that mean and variance for each class. And then we have some hyperparameters we're updating to like update these beliefs.
So if your Bayesian estimate from vision had converged to be very certain about the semantic class, and then you took a friction measurement, it's unlikely that it would change much your belief about what that class is. It's much more likely that it would now update what your belief about the friction properties of that class.
Exactly, yeah. So if you're like, there's 100% ice, and it feels like concrete, well, then it's probably going to be, well, you said it was 100% ice with no uncertainty, so like now we're going to...
Now my distribution over ice friction is now gone down.
Yeah, and so there are some hyperparameters you can tune here, for instance, like these guys and these guys. There's a bit of playing around with, so like how you tune these affects basically that. So like if you're more certain about one class, but you still have a slight belief in another, like how much does that measurement affect these outputs? So that's one of the things you can tune. Or if you're really, really sure about the class, then that, update is just going to update the class friction model. So there's things you can play around with, but it's not so, you don't have to do too many knobs.
Makes sense.
And so we were using like one set for like the door opening experiment, the semantic experiment, and the friction data set experiment.
So in the door opening experiment, what's your measurement is like the force that you're exerting?
Yeah, so the
And,
force
like,
when there's
happening?
movement.
Okay.
And so you can start with, again, like two modes. So like here, it's your uncertainty that it's push or pull. And then this would be like the
How heavy the door
is the variance force. So yeah, and then your observation is then just updating like, hey, I pushed it with 50 newtons of force and it started to open. You'd be like, okay, well then it's push.
Probably pull or an extremely heavy door.
Yeah, and so the interesting thing with this is we didn't just do it over one door. And the paper we showed like, hey, what if we do this with like 6 doors, I think, over the campus? And then it actually turns out to just be like 2 modes, but they're basically in the center together with a really wide variance. And you're like, we truly have no idea, because some doors are like 70 newtons of pull force or like 80 newtons of push force, or this one's like 5 newtons of pull force and it opens. So it's just kind of showing, what you'd expect. When you come to a door like this, you're like, let's push or pull, let me try. Okay, like same thing a human would do.
Exactly.
So it was sort of interesting. A lot of the work we've done on this too is like a lot of the math, and then you get to the experiment, you're like, oh yeah, it's kind of intuitive why it's doing this. There's another demo we have of active perception, so the robot's trying to like orient a camera to get more data about the world, and it turns out that the most informative trajectory is it just spins really fast, which is hilarious to see because it's a little platform like spinning in simulation as it moves from one area to the next.
I have a question,
sorry.
one more question.
Yes.
When you were doing your experiments, did you ever have a situation, either in the real world or in simulation, where the number of actions you could take sensing actions you could take was like a little bit larger than what you've shown here? So for example, like if I wanted to know about friction, I had like a passive action, which is to just have the camera on, or I had like an active way, which is measuring. But as far as I can tell, there weren't like, you didn't have to like walk anywhere specific to measure. You were kind of like constrained. This is not a criticism, this is just like what happened in the experiment.
Sure, yeah.
A lot of active sensing can be formulated as a partially observable Markov decision process. Do you see like a happy marriage between this kind of work and a POM-DP where your action space is a little bit larger and you might actually have to do some planning to figure out the best way to condense belief versus just being like, well, these are the tools, I'm going to use them and I'm going to see what happens to my posterior?
So I want to highlight, when we were taking these measurements, there wasn't a human in the loop, but a human was telling, like, when we were programming, they were like, okay, you're going to walk forward like a meter, take a measurement in front of you, and then we had some visual update model that you saw to like do that autonomously. We were not having the robot specifically figure out which action to take. So we were like, go open this door, like we had the model to like find the door handle, grab it, and then it would like push or pull randomly until there was movement. But for the friction model, it was like just rubbing.
Right.
And so going forward, I think like one idea is a POM-DP. The other thing I've been throwing around is this notion of like mixed integer programming, about like where in the terrain to take it, and combining these in some sort of active perception framework. So to your point, like, whatever planning method you want to use, because we're actually able to model the uncertainty in these enclosed form, right?
It seems like this would fit really nicely in like an observation function. Or even like when you open the door, like you don't try random forces and random pushing and pulling in a random sequence. You try like, okay, I'm gonna push, and then like, okay, I'm very certain, like my belief that this is push, I'm exerting a lot of force.
Yeah.
I could have to push harder, but now I'm thinking it's more likely that it's pull.
Yeah, exactly.
There's like a structure to the interaction, even with something so simple as a door.
Yeah, and so for most of in my master's and at the beginning of my PhD, I focused more on this like structural planning problem. And then at some point I ended up switching over to more of this perception. So a lot of this work focuses on solely perception. We have simplistic planning models, but like me and the team I'm working with are focusing on like how do we actually model these things from perception. I think what you're talking about is like the natural way forward of okay, well now we have these methods for perceiving these properties. How can we plan to do things like active perception where we get, do you know about information gain? Yeah, so like how can we maximize information gain? Like what, trying to learn about different properties, what active sensing modality, either with a POM-DP or mixed feature programming, will give us that max information gain. And so now that we've developed these tools, I think one of the interesting things is like how can we use these tools in different scenarios in order to do that?
Right.
Similarly, in like reinforcement learning, like can we learn autonomously how to do this? If we tell a robot the region in front of it is like maybe slippery, does it learn to actually go take a measurement or does walk around it? So these are the sorts of things that I'm really interested in now pursuing.
Yeah, okay.
Mhm. Yeah, normally it doesn't learn these skills too well. Hey, I'm Glenn Brissett. Went to UDM instead of Mila today. Oh well. Yeah, because I wonder about these skills in RL. People have not been very successful at being able to be able to encourage RL agents to generate this type of behavior. They tend to like wander around and stumble upon a plan and like, oh look, it works. Does it actually do something as engaging or skillful as like I should slow down and take some measurements here because I don't understand well enough what the future is?
So I haven't actually played around with these. These are only future directions I want to go. And so at the moment, I have a project for active perception. And you know, we're going forward and maybe focus on these reinforcement learning agents a little bit more. But I'm really motivated by some of the work that's come out recently for legged locomotion RL. And I think the missing piece for that is that those agents, to the best of my knowledge, I could be wrong, are not given property information. So I think from the exteroceptive RL stuff that I've seen, it might be like, oh, here's like a point cloud of the terrain around you, but it's not really saying like, oh, the region in front of you is slippery, the region in front of you is rocks. And then the RL agent learn different policies based on these different terrain types or different properties. So I'd be interested to see like if we actually embed that understanding and that information into these RL agents, can they learn from that? And if we're able to, update these beliefs autonomously online, like can it continually, actually be useful in the real world by continually updating its belief?
Yeah, you should have, if you've got some time, have a chat with Costa and Adriana, who've been looking at like these type of conditional policies where they're basically conditioned on something related to the epistemic uncertainty describing like the current model predictions for the future plan. It was still a bit tricky in the math and maybe a bit unstable, but it's roughly some ideas that sound similar.
Yeah, it'd be interesting to hear their perspectives.
Yeah, like risk aware RL, which I think could be like somehow related, but yeah, for the most part, those projects, they don't have such a concrete notion of risk. It's somehow meant to be more abstract and learned, which I think is just super hard.
Yeah, and I've kind of recently started to wonder if there's a nice marriage between the two. Because I think there's the fully RL side, like you do everything, like maybe exteroceptive, mostly proprioceptive to joint torques. Wonder if there's a way to combine like these model-based methods that we've done and do harder things like footstep planning or maybe some high-level waypoint generation using RL, and then using these model-based approaches and things like this risk-aware, joint torque computations now that would allow us to follow those and say, hey, maybe the way I have to move my feet is a little bit too challenging to model directly, but we can use an RL agent to estimate that. Maybe the trajectory I want to follow, we can get from an RL agent, and the lab I'm working with now, we've done that for autonomous vehicles really well. And then we marry that nicely with these more, grounded concepts in mathematics, like optimization, risk-aware analysis, and stuff like that. So yeah, going forward, I kind of wonder, similar with, the machine learning stuff and vision we've seen here, there's a nice marriage between vision and machine learning and probability theory. Can the same exist for just these more standard model-based predictive controllers that we've seen and reinforcement learning?
Mm-hmm. I have to run. I guess we're at the top of the hour. Shall we say thanks again to Parker and close it? Okay.